Welcome to the Code Navigators. Our mission here is, well, it's pretty clear. To systematically go through sections of the International Code Council code
All
books.
right.
We want to help you understand the sometimes dense contents and, maybe most importantly, how to navigate them efficiently.
Especially if you're studying for an ICC exam.
Exactly.
We're here to act as your guides, really. We're trying to extract the essential knowledge so you can gain competence quickly.
Without feeling completely overwhelmed by just the sheer volume of this material.
Yeah, I mean, these books are huge. Think of us as providing the necessary framework for mastery, turning all that volume into actionable knowledge.
Before we jump into today's chapter, we do have an important production note. This program is created using AI-assisted generation with the final production and all the oversight provided by a human code professional.
Now, a crucial legal matter that really, it has to come first.
Always.
Disclaimer. This discussion is for educational purposes only. It is not intended to be professional design or engineering advice.
That's really important.
It is. You, the listener, you must always consult the official, current ICC Code Edition and seek counsel from a qualified professional for any specific construction project or legal matter.
And we won't be stating any copyrighted material. We're just discussing the codified requirements.
And their implications for design and construction, yeah.
With that necessary context set, today we are opening up Chapter 19 of the 2021 International Building Code. This is the big one, the foundational chapter dedicated entirely to concrete.
And this is where code navigation immediately becomes a multi-volume library endeavor.
I can imagine.
What's absolutely crucial to understand right up front about Chapter 19 is that it relies so heavily on an industry standard.
Okay.
That's the American Concrete Institute, or ACI 318.
ACI 318, I've seen that referenced everywhere.
You can think of ACI 318 as the technical Bible for concrete design and construction. I mean, it contains all the formulas, all the scientific rationale. It's the how and the why.
Okay, so if ACI 318 is the Bible, what does that make IBC Chapter 19?
That's a great question. Chapter 19 acts as a sort of a local jurisdiction overlay, or maybe a massive detailed amendment is a better way to put it.
So it modifies the Bible.
Exactly. The IBC doesn't try to rewrite ACI 318. That would be, reinventing the wheel.
Right.
Instead, it provides specific rules, modifications, and most importantly for you, the learner, it provides a lot of exceptions to ACI 318.
Okay, so it's about tailoring that huge standard for specific building situations?
Precisely. These changes relate specifically to things like durability, seismic requirements, and lower-risk structures like residential homes.
Got it.
So if you're designing a concrete structure under the IBC, you absolutely must be cross-referencing ACI 318 constantly. You have to filter every requirement through the lens of IBC Chapter 19.
Okay, so let's unpack that relationship. Let's jump right into the general requirements, starting with Section 1901. This seems to set the stage for everything.
It really does. Section 1901 establishes the foundational rules for the chapter. It clarifies exactly who, what, and how this code applies, and it defines the minimum required documentation.
Starting with scope and applicability. Section 1901.1. This seems pretty broad.
It is. It lays out the breadth of the chapter, and it covers three main areas.
Which are?
First, the material quality control. Second, the structural design processes. And third, the construction methods for any structural concrete used in any structure that falls under the IBC's jurisdiction.
So it's meant to be totally comprehensive.
Exactly. It's covering the entire life cycle, from the initial mix design all the way to the final structure's performance.
And then right away in Section 1901.2, we hit that core navigation challenge you mentioned.
Yep. For plain and reinforced concrete, it states the dual requirement. Structural concrete must comply with this Chapter 19 and with ACI 318.
You can't just pick one.
You cannot satisfy one without the other. This is the ultimate two-book scenario.
Yeah.
And you have to operate knowing that ACI 318 is the default rule unless Chapter 19 specifically overrides it.
But the IBC immediately gives us the first set of what you called navigation shortcuts, the exceptions.
Right.
For someone studying, knowing when you don't have to dive into the full complexity of ACI 318, that must save a huge amount of time.
It saves immense time. Precisely. The IBC carves out these specific exemptions where its own simplified rules govern.
What's a good example?
Well, the design and construction of slabs on grade, they're often exempt from a full ACI 318 analysis.
And that makes sense.
It makes perfect sense. Slabs on grade, they typically transmit loads directly to the soil. They're not complex structural members designed for bending or shear like, say, a suspended beam would be.
So what other key sections are immediately flagged for these IBC-specific rules?
Section 1904, which covers durability, and Section 1907 on minimum slab provisions are both given specific carve-outs.
Okay.
And some other slabs that transmit vertical loads or lateral forces from other parts of the structure to the soil, they're also generally exempt from the full ACI 318 requirement.
So this is basically signaling that for these common, maybe less critical elements, the IBC gives you a more direct path.
A more direct and often less analytically intensive path than the full ACI 318 standard. It definitely simplifies life for, residential builders.
Let's move on to some specific elements. Section 1901.3 deals with anchoring to concrete.
Right.
This applies to, well, it seems like every type of fastener used to attach other things to the concrete.
It really does. Steel, wood, even facade elements, anything that connects to the concrete substrate.
So what kind of hardware are we talking about here?
It's a huge range. It covers things that are cast in, like headed bolts and headed studs, but especially post-installed anchors.
Post-installed, so those are put in after the concrete is already hardened.
Exactly, and they are incredibly common in construction. This includes mechanical anchors, things like expansion bolts, undercut anchors, screw anchors, and also adhesive anchors.
The ones that use that specialized epoxy?
Yep, the chemical epoxy, all of them fall under this.
And do all of these anchors fall under ACI 318?
They absolutely must. The code requires them to comply with ACI 318, specifically the anchoring provisions, which are found in Chapter 17 of ACI 318.
And I see it says, as further modified by the IBC in Section 1905?
Correct. We'll get into that later, but that integration just shows how critical proper fastening is. I mean, think about it. If your anchor fails, the structural member it supports also fails.
It's the weakest link in the chain.
It can be, and we'll spend a lot of time on the highly complex seismic modifications to anchoring later in our discussion.
Okay, here's where we get to a cross-disciplinary element. Section 1901.4, composite construction.
Right, when you have a hybrid system. Specifically structural steel that's designed to act compositely with reinforced concrete.
The design has to be handled in accordance with IBC Section 2206.
That's right. This is essential for structural stability because composite construction relies on sharing the loads between the steel components, like your H-beams, and the concrete slab or the encasement around them.
So Section 2206 is the rule book for making sure those two different materials work together.
It is. It details the rules for ensuring that shear connectors or other mechanisms properly transfer the load and the deformation between the steel and the concrete. It really highlights that, concrete professionals have to be aware of the steel code requirements when they're working with these systems.
Now, let's talk about the documentation, the paperwork required to ensure quality. Section 1901.5, covering essential construction documents. This seems critical.
Oh, absolutely.
If you're studying for an exam or you're acting as an inspector, this looks like your primary checklist for a plan review.
It is. These requirements are the fundamental quality control checkpoints. They bridge that huge gap between an abstract design on paper and the tangible construction on site.
So by requiring these 8 specific details on the plans,
the code ensures that the structure that gets built is the structure that was designed, and it lets inspectors verify all the safety-critical elements.
Okay, let's walk through them. It seems important to understand why each one is necessary.
Let's do it.
The first one, and it feels like the most foundational, is the specified strength of concrete at various stages. Why the emphasis on various stages?
That's the key phrase. Because structural concrete often needs to reach a certain minimum strength before you can do specific things.
Like what?
Like removing the shoring that's holding up a new floor, or applying pre-stressing forces in a post-tension slab, or even just allowing construction traffic to drive on it.
Okay, so the plans have to specify the required compressive strength, the F'(C), not just at 28 days, but also maybe at 7 days or even sooner.
Exactly. For these critical stage releases, if that detail is missing from the plans, a contractor might strip the forms prematurely, and that could lead to a collapse.
Wow. Okay, number 2, the specified strength or grade of reinforcement.
This is non-negotiable. Designers rely on the yield strength of the rebar. Grade 60, which is 60,000 psi yield strength, is common.
But there are others.
Oh yeah, you'll see grade 75 or even grade 80 used for high-strength applications. If the contractor substitutes a lower grade of reinforcement,
All the math is wrong.
all the load calculations are invalid. The element will not achieve its design capacity. The plans have to clearly state the grade. No ambiguity allowed.
Third, the size and location of structural elements, reinforcement, and anchors.
This is the geometry checkpoint. It covers the dimensions of the members, your beams, your columns, your slabs, and also the critical concrete cover over the reinforcement.
And the cover is that layer of concrete protecting the steel, right?
It's essential. It protects the steel from corrosion and from fire. An inspector must be able to look at the plan and then look at the formwork and verify that the rebar cages are correctly sized and positioned to maintain that required cover.
So a common mistake is getting that placement wrong.
Incorrect placement of reinforcement is one of the most common deficiencies found in the field. Absolutely.
Number 4 is a highly technical, long-term performance issue, provision for dimensional changes. This covers creep, shrinkage, and temperature effects.
And this point is so critical for the long-term life of the structure. Shrinkage is the volume reduction of concrete as it dries and hardens over, say, the first year. Okay. Creep is the long-term deformation of concrete when it's under a sustained load.
So it slowly sags over time, essentially.
That's a good way to think about it. And if the plans fail to account for these movements, maybe through movement joints or additional reinforcement, the structure is very likely to crack.
And then it leaks.
And it could potentially compromise its serviceability or even its structural integrity years and years down the line. This demands an understanding of material physics, not just immediate strength.
Okay, the 5th detail is for advanced systems. The magnitude and location of pre-stressing forces.
Right. So if the concrete is being actively stressed, either pre-tensioned at the plant before the pour or post-tensioned on site after,
Those forces are huge.
they are massive, and they must be clearly quantified and located on the plans. Pre-stressing is literally fighting gravity, and any misapplication of those forces can lead to immediate catastrophic failure.
So the engineer needs the plan to be incredibly precise.
Absolutely. Detailing the profile and the tensioning force of every single tendon.
6th, we're looking at reinforcement continuity. Anchorage, length of reinforcement, and the location and length of lap splices.
Right. Load paths in reinforced concrete rely on tension being transferred seamlessly from one piece of rebar to the next.
Through that lap splice.
Through a lap splice, where two bars overlap. Yeah. That overlap must be long enough, according to ACI 318, to transfer the full tension force without slipping.
And if the plans don't specify that, or the contractor cuts it short?
The structural elements can fail right at the splice when they go into tension. It's a critical failure point.
7th, the type and location of mechanical and welded splices of reinforcement.
So lapping is common, but sometimes you have space constraints or just very high forces that require mechanical couplers or even welding.
And those methods affect the steel's performance differently.
They do. Welding has to be very controlled because it can weaken the steel unless you follow specific low-hydrogen procedures. And mechanical couplers have to be the correct type to develop the full required strength of the bar.
So the plans have to call out these specialized details.
They have to mandate them to ensure that the rebar connection is verified as being just as strong as the rebar itself.
And finally, the 8th requirement covers the detail and location of contraction or isolation joints. Why are these plan weak points so important?
Because concrete will crack. It's just a fact due to shrinkage and thermal movement.
So if you don't tell it where to crack,
it will create unsightly, leaky, and structurally undesirable random cracks all over the place. Contraction joints are designed to control those shrinkage cracks.
like the lines you see in a sidewalk.
Exactly. And isolation joints allow movement between different structural elements or between the concrete and an adjacent material, like a column base separating from a slab.
So specifying these joints is really fundamental to the serviceability and, frankly, the aesthetics of the finished structure.
It absolutely is.
That detailed breakdown really shows why those 8 elements are the backbone of quality control for any set of concrete construction documents.
They really are.
Let's transition now into the quality control mechanisms specified in the code. We're talking inspections, tolerances, and materials, drawing from sections 1901 and 1903.
Right. This is where the paper design meets the messy reality of the construction site.
I like that.
Section 1901.6 on inspections and tests. It serves as the legal mechanism. It just references the code's overarching quality control chapter, which is chapter 17.
Okay, so it points you to another chapter.
It does. For all structural elements, your beams, columns, walls, special inspections and tests have to adhere to all of Chapter 17's requirements.
So what does that mean practically on a concrete job site? What's an inspector looking for?
It means specific phases must be verified by a qualified special inspector. Chapter 17 mandates continuous special inspection for things like the placement of reinforcement and pre-stressing tendons.
Continuous, so they have to be there the whole time.
The entire time that work is happening.
Mm-hmm.
And then it requires periodic special inspection for things like concrete placement and visiting the batching plants. And the code makes it explicit. Tests, like your compressive cylinder tests, and inspections are required for structural elements to show compliance with the specified design strength and material quality. It is not optional for structural concrete.
Let's move to structural tolerances, section 1901.7. This is all about dimensional accuracy. Why do we need a whole separate standard for how close the finished product has to be to the plans?
Because concrete is poured as a fluid, it's just really easy for dimensions to shift. A wall might be slightly out of plumb, or a beam might be slightly undersized,
Or the rebar might be placed a little too high or too low.
which affects your concrete cover. Tolerances regulate this acceptable deviation from the plans. Section 1901.7 relies on the ACI 117 standard, which is the universally accepted specification for dimensional tolerances in concrete construction.
And if the deviations go beyond those ACI 117 limits?
The structural integrity could be compromised.
I see the IBC breaks tolerances down into cast-in-place and precast categories. What are the exceptions for cast-in-place concrete in 1901.7.1?
Okay, so the standard rule is you have to comply with ACI 117.
Yeah.
But there are two critical risk-based exceptions that a code navigator really has to internalize.
That's the first one.
Exception number 1. Group R3, detached 1 or 2 family dwellings, are not required to comply with the strict ACI 117 tolerances.
Okay, that's a big one.
It's a classic risk-based regulatory concession. For a single-family home foundation, the consequences of a foundation wall being an inch or 2 out of plumb are, they're localized and they're manageable.
Not like the sheer walls of a high-rise building.
Exactly. The code recognizes that the cost of applying high-precision tolerances doesn't justify the marginal safety benefit in this low-risk context.
And the second exception is related to the placement method.
It is. Shotcrete, that's the pneumatically projected concrete,
Mm.
is also not required to comply with the standard cast-in-place tolerance requirements.
Which seems like a practical exemption.
It's purely practical. Because shotcrete is applied with a high-velocity nozzle onto a surface, trying to achieve the really tight dimensional tolerances specified for formwork-defined concrete is often impossible.
So the IBC just exempts it.
It exempts it from this section, 1901.7.1, though it still has to meet the placement requirements that are back in ACI 318.
Do those same R3 exceptions apply to precast concrete?
Yes. For precast concrete tolerances in section 1901.7.2, the default is ACI 117 compliance. But similarly, Group R3 detached 1 or 2 family dwellings are accepted from these requirements.
So again, that same theme.
That same recurring theme. The IBC prioritizes regulatory relief where the structural risk is low, which helps streamline construction for smaller projects.
Let's shift gears to materials and terminology. Section 1902.1 deals with the coordination of terminology. This seems like it's just about making sure everyone is speaking the same language when juggling multiple code books.
And it's a critical legal anchor. It states that terminology used in ACI 318 and ASCE 7, which is the minimum design load standard, shall be used in this Chapter 19, unless the IBC explicitly provides its own definitions right here in Section 1902.
And that prevents conflicting technical definitions.
It does. It ensures that terms like development length or special moment frame mean the exact same thing, whether you're reading ACI 318 or Chapter 19.
Moving into Section 1903, specifications for tests and materials. The general requirement, 1903.1, seems to just reinforce that materials and procedures have to comply with ACI 318.
Right. ACI 318 has all the ASTM standards for cement, for aggregates, water, admixtures. The IBC simply confirms ACI 318's authority here.
But then the IBC steps in for specialized concrete types.
It does, for those that might require different compliance standards.
And two specific materials are called out here in 1903.3 and 1903.4. First, glass fiber reinforced concrete, or GFRC.
GFRC under 1903.3 has to comply with the PCI M&L 128 standards. GFRC is a thin, high-performance material you see a lot for architectural cladding or non-structural elements.
So since it's not traditional structural concrete,
The IBC directs the designer to the specific industry standard from the Precast Prestressed Concrete Institute that governs its unique material composition and its manufacturing.
and second, flat wall insulating concrete form, or ICF systems.
These systems are popular for their energy efficiency. They use those modular, interlocking foam blocks that stay in place as permanent formwork when you fill them with concrete.
Okay.
Section 1903.4 requires ICF systems to conform to ASTM E2634. This standard ensures that the entire system, the foam, the ties holding it all together, and the concrete performs safely as a single unit.
Addressing things like fire and structural performance that are unique to ICFs.
Exactly. For the learner, this is a clear sign that specialized materials require specialized compliance standards that are outside the main ACI 318 framework.
That brings us smoothly into Section 1904, which governs one of the most important non-strength characteristics of concrete: durability.
Right. This is all about ensuring the concrete lasts when it's exposed to environmental hazards.
So freezing, chemicals in the soil, that sort of thing.
All of it. Durability dictates the concrete mix design based on the anticipated exposure. ACI 318 defines these exposure classes, like F for freezing and thawing, S for sulfate exposure from soil or water, and W for water exposure or corrosion risk.
And structural concrete, under 1904.1, has to meet these.
It must meet these stringent durability requirements of ACI 318. For example, it might require air entrainment for freeze-thaw resistance and a low water-to-cement ratio to reduce permeability.
But here's where the IBC provides a potentially massive cost-saving exception, specifically for certain low-risk residential structures.
This is a critical detail for residential contractors to know. For Group R2 and R3 occupancies that are not more than 3 stories above grade plane, a reduction in the required minimum compressive strength is allowed.
For which elements?
For specific elements like basement walls, foundation walls, exterior walls, and other vertical surfaces that are exposed to weather.
How much relief does this exception actually provide?
The required compressive strength, your F'(C), can be set at not less than 2,500 psi, which is 17.2 megapascals.
But there are conditions.
2 big conditions. First, the concrete must still satisfy the required ACI 318 exposure class requirements. And second, the anticipated weather exposure cannot be classified as severe.
So let me get this straight. If I'm building a 2-story house in a northern climate that has severe freezing and thawing, I can use 2,500 psi concrete, but I still have to include adequate air entrainment. Is that right?
Precisely. The code grants a concession on the raw compressive strength, but it provides zero concession on the durability mechanisms.
Okay, that makes sense.
The 2,500 psi is often perfectly adequate for the compressive loads in these low-rise structures, but the concrete must still be formulated to resist that environmental attack.
Meaning the mix design still has to have the right water-to-cement ratio and air content defined by ACI 318.
You got it. It balances safety with practicality.
Now, what about non-structural concrete, which is covered in 1904.2? Things like pavement, patios, slabs, where load-bearing isn't the main function.
Even those non-structural elements have to hold up against the environment. The code requires the design professional to assign a nominal compressive strength to non-structural concrete based on its anticipated exposure.
So there are still minimums.
Oh yeah. Minimum compressive strengths are defined for classes F1, F2, and F3 in accordance with ACI 318. For example, Class F1, which is the least severe exposure, still requires a minimum compressive strength of 2,500 psi.
Because even a sidewalk that isn't holding up the building still needs to resist surface scaling and cracking from winter salting.
Exactly.
Let's transition from materials back to structural elements, specifically the structural walls detailed in Section 1902. We have the standard wall types, detailed plain, ordinary precast reinforced concrete, and ordinary reinforced concrete shear walls.
And those ordinary walls are designed using standard ACI 318 methods, relying on strength calculation. However, the crucial wall type for high-risk zones is the special structural wall, which is defined in Section 1902.2.
When does a standard wall graduate to a special structural wall? What's the trigger for those intense seismic requirements?
The rule is very precise. If a concrete shear wall is required to resist seismic forces as defined in Section 12.8.6 of the ASCCN standard.
Which calculates the design shear force?
Right. If it's resisting those forces, it is automatically defined as a special structural wall. That classification immediately triggers the need for ductile detailing.
Ductile detailing. You mean you need it to bend, not break?
Exactly. In a severe earthquake, we need the wall not just to hold, but to bend and deform without a sudden brittle failure.
And what are the implications of being classified as a special structural wall?
They must comply with incredibly stringent detailing requirements. You find those in sections 18.2.4 through 18.2.8 and 18.1 of ACI 318.
What do those sections govern?
Things like confinement reinforcement. That's extra hoops and ties in the boundary elements of the wall, and strict limits on how you calculate shear strength. The whole goal is achieving high ductility, ensuring the wall can absorb energy through stable, inelastic deformation.
So that distinction, ordinary versus special, is purely driven by the seismic load path.
Entirely. The IBC defines a load condition using ACE7, which then dictates the necessary structural detailing from ACI 318. It directly connects the physics of the earthquake to the rebar cage inside the concrete.
This leads us to what sounds like the most complex part of the chapter, Section 1905, Modifications to ACI 318 for Seismic Design.
Yeah, this is where the IBC asserts its final authority over the reference standard.
So if you're practicing in a high seismic area,
If you are practicing in seismic design category D, E, or F, this is the most critical navigation section in all of Chapter 19. Section 1905 dictates extensive modifications to ACI 318
why?
because it recognizes that the ACI standard by itself doesn't always provide the necessary safeguards against the brittle failure modes that are induced by high seismic forces.
Let's look at an example. How does the IBC treat concrete elements that are not designed to resist the primary seismic forces, according to 1905.1.2?
This is a nuanced but really crucial point. For structures in seismic design category D, E, or F, ordinary structural concrete elements that are not part of the designated seismic force-resisting system.
Like a non-load-bearing filler column or something.
Exactly. They do not need to satisfy the full, intense requirements for special elements like intermediate moment frames.
But they can't just be plain concrete either, I'm guessing.
You are correct.
Yeah.
They're exempt from the special detailing rules, but they still have to be detailed to survive the shaking. They must satisfy the requirements found in ACI 318 sections 18.4, 18.5, 18.10, and 18.11.
And in simple terms, what does that mean?
It means they still need minimum reinforcement ratios, proper anchorage, and detailing that prevents brittle shear failure, even though they aren't carrying the main lateral load. The code recognizes that everything shakes, and everything needs a minimum level of resilience.
Section 1905.1.3 focuses on structural element behavior during high deformation, modifying ACI 318 section 18.5. This gets directly to that engineering concept of ductility.
It does. It requires structural members to be capable of maintaining a percentage of their design strength at the deformation induced by the design displacement.
Can you break that down?
Sure. Imagine a concrete column bending significantly during an earthquake. This section demands that the column must not just maintain its load, but it has to sustain that load while it is bent. If the designer can't demonstrate this capacity, this ductile performance, through calculation or testing, then they must use Type 2 mechanical splices for all the reinforcement connections.
What makes a Type 2 mechanical splice so critical here?
A Type 2 splice is designed to develop the full specified tensile strength of the bar. That includes its yield strength and its strain hardening, even when it's subjected to cyclic loading.
So back and forth earthquake movement.
Right. Unlike a standard lap splice or even a Type 1 mechanical splice, the Type 2 ensures that even when the material is stressed well into its yield point, the connection remains robust. It's the absolute highest level of connection assurance required when ductility is paramount.
Now, let's address the tricky topic of using plain concrete in seismic zones. That's covered in 1905.1.4. Since plain concrete is inherently brittle, it's generally forbidden in seismic design category D, E, or F.
That's the rule. Structural elements of plain concrete are just not permitted where high ductility is required. I mean, if the earth moves violently, you need steel to hold the concrete together.
But the code provides some crucial, very constrained exceptions for foundations.
It does.
What's the first major exception for basement foundation walls in residential structures?
Okay, this is strictly for foundation walls supporting 2 stories or less of light frame construction in seismic design categories A, B, C, and detached 1 and 2 family dwellings.
Because very specific, and what are the dimensional limits?
There are a few. First, the wall cannot exceed 8 feet in height. Second, the ratio of its height to its thickness must be no more than 7:1.
So a stocky wall.
A very stocky wall. Third, the wall can retain no more than 4 feet of unbalanced backfill. And fourth, it has to satisfy the minimum vertical reinforcement requirements of ACI 318, section 14.8.
That 7:1 height-to-thickness ratio seems key to preventing a slenderness failure.
It is. It's to ensure the wall is stocky enough to handle any load, even without primary reinforcement. It prevents the wall from buckling or failing catastrophically in a brittle shear mode.
And the second major exception is for isolated footings.
Right. Footings supporting pedestals or columns are permitted, provided the projection of the footing beyond the face of the member it's supporting does not exceed the footing's own thickness.
Why that geometric restriction for isolated footings?
If the footing projection is less than the thickness, the footing primarily acts in direct compression and shear right near the column face. This minimizes the bending moment,
Which avoids high tensile stresses in the bottom of the footing.
which is exactly where plain concrete is weakest and most prone to brittle cracking. The code is essentially forcing the footing into a low-stress, compression-dominated failure mode where it's strongest.
Let's delve further into the reinforcement details required for these plain concrete footings, still within section 1905.1.4. Even if they're technically plain, seismic zones often require some minimum steel.
They do. For plain concrete footings that support walls, specific minimum reinforcement is mandatory. This is to ensure crack control and continuity across the foundation perimeter, which is especially crucial in corners.
What kind of steel are we talking about?
You have to provide longitudinal deformed bars, a minimum of 2 bars, and those must be a minimum size of number 5 bars, provided in both the top and the bottom of the footing.
That sounds like standard practice, but the code adds a specific calculation requirement for the amount of steel.
It does. A calculation has to be performed to ensure the ratio of the reinforcements area, that's A subs, to the growth cross-sectional area of the footing, A sub G, is at least 0.0025.
And what does that ratio do?
It defines the minimum density of steel that's necessary for adequate crack and movement control. And on top of that, the maximum bar spacing is limited to 18 inches.
And for thicker footings?
For thicker footings, those 2 number 5 bars have to extend 6 feet beyond the projection of the footing. This extensive reinforcement ensures the foundation acts as a single, tied, continuous unit, resisting differential movement.
And as always, what are the exceptions to these specific footing reinforcement requirements?
Just like before, the code provides regulatory relief for the low-risk category. These specific longitudinal reinforcement requirements are not required in seismic design categories A, B, and C for detached 1 and 2 family dwellings.
Okay.
They're also waived for basement foundation walls that meet those strict height and thickness limitations we just talked about, or for foundation systems with a plain concrete footing and a plain concrete stem wall, provided there's at least 1 number 5 bar at the top and 1 at the bottom of the footing.
Let's shift dramatically now to anchoring, section 1905.1.8. This modifies ACI 318, Chapter 17, and it focuses entirely on anchor requirements in high seismic zones.
Right. Categories C, D, E, or F. Anchoring a light frame structure to a concrete foundation is a key failure point in earthquakes.
So this modification introduces special checks for anchor design strength when those seismic forces get too high.
Exactly. It defines 3 main scenarios for when the design has to adhere to rigorous seismic checks rather than simplified prescriptive methods.
And the critical threshold here seems to be 20%.
It is. The first scenario deals with anchor tension. If the tensile component of the strength level earthquake force on an anchor exceeds 20% of the total factored anchor tensile force for the same load combination,
Then you have a problem.
then the anchor tensile strength has to be checked using specific seismic design procedures detailed in ACI 318.
So if the anchor is mostly just seeing gravity load, the simple check is fine. But if seismic uplift starts driving more than 1/5 of the tension, the rigorous seismic design calculation gets triggered.
Precisely. This ensures the anchor's capacity for complex failure modes like pull-out, concrete cone breakout, or bond failure is verified against that high seismic demand.
And the other 2 scenarios apply the same 20% threshold to shear forces.
They do. The third scenario says, if the shear component of the strength level earthquake force on the anchor exceeds 20% of the total factored anchor shear force, you have to do the same thing.
You have to check the design shear strength according to the seismic provisions.
Correct. This threshold recognizes that when earthquake forces significantly dominate the connection design, you must perform a detailed, rigorous analysis of how that anchor interacts with the concrete to prevent a brittle failure when it's highly stressed.
But there's a crucial deferral here, right? We're talking about wood frame structures being anchored to concrete.
Yes, and this is a big one. The code provides an exception to these rigorous seismic strength checks, specifically for the in-plane shear design of anchor bolts that attach wood sill plates and wood track of bearing or non-bearing walls of light frame construction to foundations.
Which is the most common residential anchoring scenario there is.
By far. So if you're anchoring a standard wood sill plate, you get to use a simplified standard.
You do. The IBC directs you away from ACI 318's complex seismic checks and sends you back to the American Wood Council's National Design Specification, or AWC NDS, Table 12E, for determining the allowable in-plane shear strength of these exempt anchors. That's a massive navigation relief. For light frame shear, you consult the Wood Code, not the complex concrete seismic provisions.
It's a classic code efficiency move, using the most appropriate and often simpler standard for that material interaction.
Makes sense.
The code also provides other exceptions for light frame construction when attaching anchors that are 1 inch in diameter or smaller, provided they meet certain requirements related to shear strength. They often rely on prescriptive methods rather than a full seismic analysis.
Let's shift to the simplest foundations covered in the chapter, Section 1906, Plain Concrete Footings for Group R3 Occupancies.
This section offers a simplified prescriptive footing designed specifically for Group R3 1 and 2 family dwellings and detached accessory structures, as long as the construction is light frame.
So this is for jurisdictions that allow plain concrete footings in this specific context.
Exactly.
What were the primary dimensional requirements under 1906?
For these simple plain concrete footings, the required thickness is a minimum of 6 inches. And critically, the footing cannot extend more than 4 inches outside the face of the wall or stem wall it's supporting.
And that tight geometric constraint, again, is to prevent cantilevered projections.
Right, ensuring the footing stays primarily in compression, again, avoiding that tensile failure that plain concrete is so bad at.
Finally, Section 1907 covers minimum slab provisions, defining the minimum standards for ground-supported slabs.
Section 1907.1 dictates the minimum thickness, which is at least 3½ inches. And beneath the slab, the code requires materials for moisture control.
Which is the mandatory vapor retarder.
That's right. Generally, a vapor retarder is required. This has to be a minimum 6 mil polyethylene vapor retarder, placed over a 6-inch base material layer with all the joints lapped not less than 6 inches.
And that barrier is crucial for preventing moisture migration from the soil into the conditioned space.
Absolutely.
That vapor retarder requirement is pretty standard practice for conditioned spaces, but the code offers 5 critical exceptions where it is not required. Knowing these seems like a key navigation shortcut.
It is. Exception number 1. Detached structures that are accessory to Group R3. So garages, storage sheds, utility buildings.
Since they're unconditioned spaces, moisture migration isn't considered detrimental.
Correct. Exception 2 is for unheated storage rooms that have an area of less than 70 square feet. Again, small, unconditioned spaces get a pass.
Exception 3 seems useful for commercial or industrial applications.
It's very useful. It exempts buildings or areas where moisture migration through the slab from below won't be detrimental to the intended occupancy. Think of a covered outdoor loading dock, or maybe a facility that's designed to handle wet processes where moisture is just irrelevant to the operation.
Okay, exception 4 applies to exterior elements.
Right. Driveways, walks, patios, and other exterior flat work that won't be enclosed at a later date are exempt. Since they're exposed to the elements anyway, a vapor retarder would be redundant.
And finally, exception 5 is a bit of a catch-all.
It is. We're approved by local site conditions. This gives authority to the local code official to waive the requirement if, for example, the foundation is built over highly permeable, well-drained gravel where moisture migration is demonstrably negligible.
That covers the ground-level elements. To wrap up the specifics, Section 1908 deals briefly with shotcrete.
And it's very brief. Section 1908.1 simply states that shotcrete, which we mentioned earlier regarding tolerances, shall be in accordance with the requirements of ACI 318.
So the IBC just defers entirely to the ACI standard.
Completely. For the specific mix, placement, curing, and testing requirements of pneumatically applied concrete, ACI 318 is the sole authority.
So we have explored the entirety of the 2021 IBC Chapter 19 on concrete, from the documentation requirements all the way to the specialized seismic modifications.
We have. And I think the biggest navigation challenge we've highlighted is recognizing that this chapter acts primarily as a series of specific requirements and crucial modifications to ACI 318.
You have to treat them as a pair.
You do. If you're preparing for an exam or designing a structure, you have to treat Chapter 19 as the master checklist that directs you to the necessary sections of ACI 318 and ASCE E7.
And a key takeaway for me is how certain low-risk structures, particularly R3 detached dwellings, often enjoy these specific exceptions for inspections, tolerances, and even foundation requirements.
Definitely.
So when you're studying, it seems like you should focus intensely on those 8 key details required in construction documents from Section 1901.5 and understand the failure mode associated with neglecting each one.
Absolutely. And perhaps most critical are the extensive seismic modifications in Section 1905. You have to memorize the precise conditions that require that increased scrutiny.
Like the 20% threshold checks for anchor tension and shear in high seismic zones.
That's a perfect example. That's where the IBC forces a design calculation that goes beyond the basic ACI 318 standard, all to ensure maximum resilience against ground movement.
If you found this explanation helpful in navigating the code requirements, you can support our show and future content creation by visiting the Patreon link provided in the show description.
Your support really helps us continue providing this level of detailed analysis and code navigation.
As we conclude, considering the inherent brittleness of concrete versus the modern demand for seismic safety, we explored how the IBC treats a plain concrete element drastically differently depending solely on the structure's assigned seismic design category.
Right. Prohibiting it in high-risk zones, yet permitting it with very specific dimensional restraints in low-risk zones.
And that dichotomy really illustrates why mastering the code exceptions and the underlying risk philosophy is just as important as knowing the general rules.
It really is. Something for you to mull over until next time.